video. So this is in the first part of, or first video, I guess, of two that I'm going to be making while I'm away. So in this first one, I'll just let you know what I'd like to cover. So first of all, we're going to be looking at interpreting the slope and the y-intercept of the regression line. So that's the least squares regression line, the same one that we've been working on. But that's just looking at the A and B values and actually describing what they mean. We're then going to have a look at making predictions using that rule or that equation, y equals a plus bx, and obviously rounding to the appropriate number of significant figures or decimal places, and finding the RV given the EV or finding the EV given the RV. So I'll show you what I mean by that in a minute. I also want to discuss what interpolation and extrapolation means and go through an example of that with you, and finally show you how to calculate this thing called a residual. So I'll get started. To begin with, we have had a look at how to calculate A and B, so how to get the equation of the least squares regression line. But what we haven't yet done is actually describe what that means. And this is a skill that you are going to have to do when you do something called a regression analysis. Which, I mean, you will do that in the very next lesson. So that's coming up very, very shortly. To start with, I wanted to describe the slope, and you'll see that there is a definition, I guess, or a bit of a description of what the slope means, but this is going to be much easier to do when you actually have proper variables that you're looking at. So what the slope indicates is the change, or the average change, I should say. Now this could be an increase or a decrease. When your slope is positive, it will be an increase. When your slope is negative, it will be a decrease, which is why I've said increase or decrease here. Either of those could be happening. So it's the increase or the decrease in the response variable, so the RV. This is very important. It is for each 1 unit increase of the EV. Now the reason this is if I might just go to another little diagram if I can. If you have a look at this here, this is a line fitted to some data. I just did it by eye. But if I have a look at the slope, what that is the rise over the run. Now, if I have a look at what that is, say this here was, I'm going to just for argument's sake say it's 1 unit, and say this was 3 units. The rise over the run would be 3 over 1. Now what this means is it's rising, the RV is rising by 3. For each, as we've got over 1. It's rising by 3 for each 1 unit increase in the EV. This is a little bit slow. Now when you get your slope, you're not gonna have it as a fraction like this. As an example, your slope might be 0.25 or something like that. We usually have a lot of decimals, so what this would mean is really it's 0.25 over 1. So that means that your line is rising by 0.25 for each 1 unit increase in the EV. If it was negative 1.28, again, express that over 1. This is the rise over the run. In this case, because it's negative, it's actually decreasing by 1.28 for each 1 unit increase of the EV. So when you're talking about the EV, it's always an increase of 1 unit. The RV, well, that's going to be indicated by whatever the slope is. Might be positive, might be negative. Again, that just indicates whether it's an increase or a decrease. I'll get back to my screen that I had before. Here we go. I'm going to have a go at doing that in a second using the variable so I can show you what I actually mean. The second thing that we interpret is the Y-intercept, which I guess is a little bit easier because basically the Y-intercept, it's always going to occur when your EV is 0. So all we have to do is say when that variable is 0, the line, the regression line predicts what the RV will be at that particular point. I'll show you what I mean. here we have some data. Now we want the least squares regression line to begin with. That's part A. We're going to write the coefficients to 4 significant figures. So I'll go to my calculator. I have already entered this data in. There it is there. And to get my least squares regression line, I go menu 4, 1, 4. Okay, this data is day of the experiment and then the number of bacteria. So I am going to go ahead and put days in the EV. So what I'm suggesting is that the number of days that the experiment has been running will is somehow explaining how many bacteria there are. So days and then bacteria, and I'll press enter. Okay, here is my A value and my B value. Now I want 4 significant figures. So 202.5, that's already to 4, and 206.3 when I round this one, round that 2 up to 3, because the next value is 5. So I had 202.5 was my A value. And it's positive, my B value is positive, 206.3. Now that's multiplied by the EV. So this is in the form y equals A plus BX. All right, we want to actually interpret these two. Here's our A value and here's our B value. So we're interpreting the slope to begin with, and that's that one just there, that's B, and this one is A. So what does the slope indicate, or what does it estimate is another word that you can use. It estimates that every time the EV increases by 1, so every extra day, the number of bacteria is increasing, because it's positive, by this amount. So the slope indicates the number of bacteria is expected or estimated increase by, so we state by how much? 206.3. And then we also need to say what's happening with the EV. So we can't just say it's expected to increase by this. You want to say, well, what's happening? It's each increase of 1 on the EV, so it's each day in this case. If, say, that was age and it was in years, you'd say for each year. If it was in seconds, you'd say each second, or for 1 second increase. Something along those lines. But you do need to specify that it is for each one, or for 1 unit. The Y-intercept, like I said, is a little bit easier, because what it is if we have a look up here, when your EV is 0, so when you have days equal to 0, your Y-intercept, or your A value, as you can see, is 202.5. So when days equals 0, if I substitute 0 into here, I'm going to have number of bacteria is 202.5. So the Y-intercept actually estimates that initially, or when day equals 0, the number of bacteria was, and we have a look, 202.5, wasn't it? There it is, 202.5. Now we're going to have a go at this again in a second, because it is important we do it with some different variables. But every time you interpret the slope, you'll be saying this same thing. You'll be saying that it estimates, or it indicates that the RV is increasing or decreasing by a certain amount, and it's per 1 unit of the EV. Every time you interpret the Y-intercept, you will always say that it estimates, or the Y-intercept estimates, that when day equals 0, when temperature equals 0, when age equals 0, whatever it might be, the RV is equal to this. Now, if there's a unit involved, do write it down as well. This one wasn't because it was just the number of bacteria. We're going to have a go at that while we do this next bit, which is making predictions. Now, you're going to be doing this all the time. Whenever you are making a prediction, you're basically substituting a value into your rule. A value into the rule. Just make that a little bit more clear. Okay, here we have some data, and we have number of animals, number of visitors, and we've actually been given the rule. Here it is here. We've been given the equation for this particular relationship or association. What we want to do, you'll see it says use the equation to predict the number of visitors to the nearest whole number when there are 2 live animals on display. So here it's talking about animals at an, well, you can read it, at an exhibit, whether there's enough or whether there are some live animals there. That is obviously going to draw more visitors, hence why we have a positive relationship here. So all we need to do is use our rule and substitute what we have been given into that rule. So we were given that there were 2 live animals. So you'll see here that I substituted 2 for number of animals. I then will calculate that. So you should have your calculator with you. You can type it in and calculate it with me. But I got 128.83 and we wanted to the nearest whole number. So I'll just jot down what I got. To the nearest whole number, that would be 129 animals. Oh, sorry, visitors, not animals. So we predict there would be 129 visitors if there are 2 live animals on display. Now what I want you to do is, instead of typing this out again, just copy down what you have in your calculator and change the 2 to a 10. When there are 10 animals on display, you'll see we expect more visitors. In fact, we expect to the nearest whole number 517 of them. So what we've just done is made a prediction using our least squares regression line. That's what the regression line is. It's not an exact, it's not going to give us the exact amount of visitors that that there will be. It's not about that. It's not fortune telling. What it is giving us an estimate or a prediction using the data that we have. Sometimes you might need to do this. You might be given, say, the RV value. In this case, we want more than 500 visitors. And what we want to do is work out how many animals. So as you can see, I've just substituted 500 in for visitors. And what I'll do now, I have my calculator in front of me. You should have it as well. I'm going to use solve. So just type in A for animals and do comma A. And as you can see, I got this. Therefore, nearest whole number, we need at least 10 live animals on display. Now I mentioned before that we would try looking at the slope in the Y-intercept again, and that's what we're going to do now. So let's have a look at the slope to begin with. You'll see it's here, 48.5. So what is that actually telling us? It's telling us that there's, it is an estimate, of course. It estimates that the number of visitors, now because it is a positive slope, I now say increase by whatever the slope is, so it's 48.5 for each additional, and remember we're talking about the EV here, and it's live animal on display. So again, like we did before, it estimates the RV will increase or decrease, in this case increase, by whatever the slope amount is for each 1 unit, so that's 1 additional animal on display. The Y-intercept, well, when animals equal 0, how many visitors are we expected to have? Let's have a look at the rule. When this number here is 0, that's going to be 48.5 by 0. We're left with number of visitors is 31.83. So it estimates when there are 0 or no animals, the number of visitors will be, remember it's just an estimate, 31.83. So there's another example of how we interpret that slope and the Y-intercept. Now when you do a regression analysis, you will be required to do this. So you are going to need a bit of practice with it. I just wanted to mention this just briefly. There is a difference in predictions that we are making. So a lot of what we've just done, the predicting, we've been given an EV or an RV, and we've used that to create a predicted value. Now, when you do this and you're working with a value that is inside the range of your data, so it's in between your lowest number and your highest number in that variable, we call that interpolation. Now, the reason we have 2 types is one is a little bit more reliable than the other. When you're doing interpolation, it's actually, you can be quite confident that your value that you've interpolated, so that predicted value, is fairly accurate, especially if your R value is really, really high, or your relationship is really, really strong. That obviously means that the dots that were really clustered around the line, that means that the actual data was pretty close to your predicted values. Now, when you are making a prediction and it's outside of the data range that you're working with, we call that extrapolation. Now, extrapolation is a little bit problematic. The problem with extrapolation is when you go beyond the line, or you go beyond the data, you'll have a look at this diagram here. It might make a little bit more sense. See how the lowest of my EVs finish here and the highest finish here. Lowest in the RVs is that one there and that one across there. If I make any predictions outside of that data there, I actually am making an assumption. I'm making an assumption that, first of all, it's reasonable to extrapolate. So if you go too far this way, as an example, you'll see that you get to negative age. Now, that's not reasonable. We don't actually talk about age being negative. So that's an example of where it wouldn't really make sense to go too far away from this data. The second issue is that we're making an assumption that the data is linear there. Now, we don't know what happens with the data after this particular point. We don't know whether the dots continue going down like this, or perhaps after a certain point, they start going up like this. We have no idea what goes on because we don't have any data beyond that point. Hence why extrapolation can be sometimes a little bit unreliable. If you have a look at this, this is a classic example. We have height, it's in inches, it's obviously American, and we have time in years. Now, if you consider from this age, so about 1 up to 12, which ends about there, you'll see that we have a fairly linear growth. What happens after that, however, is it's going to stagnate. It's going to be more like this and eventually pretty flat. So what we have here, why is this question here, what are the problems associating with this, with extrapolating from this, is that we cannot be sure that the linear relationship or linear association, I like to use that word a bit more, linear association continues beyond, and as you can see, beyond about 12 years. And of course, we know with height, obviously your growth is going to slow. So we know that this particular line here is not going to continue up like this and keep going on forever. So generally, we should be more confident with interpolation, so predictions made through interpolation rather than extrapolation. The correlation coefficient is obviously very important here as well, because if you're working with a really weak association, then obviously your predictions aren't going to be as reliable either. I'll run you through this one here before we finish off with residuals. So I've got age and I've got height. So again, classic example of where extrapolation is problematic. So I think I've already put this data in. I hope I have. Pretty sure got it here. Yes. Okay. So I'll just double check that I've put it in correctly. I've got 1, 3, 5, 7, 9, and then 11. Beautiful. And then I'll just check this. Looks all right. All right. So I've got my data in there. I want the least squares regression line. So again, menu 4, 1, 4. And what I want to do is put, obviously age is going to be explanatory here. It's going to explain our height. So I'll put that in the RV and press enter. I have got 55.62. Now I just want to check, I think I said to three significant figures. So I'm going to have 55.6 and I'm going to have 9.23. So 55.6 plus 9.23, and that's multiplied by the age. Okay, next step. We want to know whether these are interpolating or extrapolating. So what we can do is, let's have a look. For 2 years, so age of 2, have a look at your data. Your lowest is 1, your highest is 11. So 2 is within the range. Interpolation. Have a look at 6. Is it within the range? Yes. 12 years, however, as you can see, is extrapolating. And why? Because our data ends at 11 years. So, of course, we're going beyond the data that we've got. To get our height, because we have been asked now to find the height, I'll just call it H, 55.6 plus 9.23 by age of 2. You can do that on your calculator. I'll just write out the workings quickly for these and we will evaluate. So by 6, and this one is 55.6 plus 9.23 by 12. So make use of the copy and paste function on your calculator, because it means you don't have to type it in over and over again. You just need to change the last number. So the first one, what do we want? 2 decimal places. So 74.06. Now that's measured in centimetres. Copy it down and change the 2 to a 6. And I've got, 110.98 in centimetres. And finally, we change the last to a 12. And we've got 166.36 centimetres. Now that is extrapolating. So that last one there, we can say is less reliable. Now you can have a go. You can change that last number there, the 12, as an example, just to show you how extrapolation is unreliable. If I change that to 24, I get 277.12 centimetres. So that's obviously ridiculous for a 24-year-old to be that tall, 2.77 metres. All right, so again, this one though is in terms of height, so we can just check that. Have a look at 55 centimetres. Now that our lowest was 60 centimetres, so that's actually extrapolating. 132, that's in the range, so that's okay. And the 168 also extrapolating. So you can write it out in full if you like. I'm just being a little bit lazy. All right. Now I want to know the age. So if I go, height is 55 this time. Just zoom it up a bit so I can see the rule. 55.6 plus 9.23 by 12. All right, so let's put that in. Menu 3.1, 55 equals 55.6 plus 9.23 by... Oh, what am I doing? I've put the 12 in. That was a mistake. So I realised as I'm typing into my calculator, I wanted age, so A equals. So times by A, comma A, and I've got, what's going on here? Something's not right. Ah, no, something is right because I was extrapolating. Now, just fix that because that should be like that. Notice I get a negative. Now, why have I got a negative? Because this was actually extrapolating beyond the data, and sometimes this can happen. Doesn't mean that your prediction's wrong, but as you can see, it is unreliable. Now, what I want you to do is finish these off by solving, and I'm going to run and grab my laptop charger because I'm looking at my battery and it's going to die very, very soon. So I'll just write this out. And what you can do in the meantime is solve for A. What you can also do is have a look at the next question and answer which of those 3 predictions is most reliable and why. Okie dokie. Now we're plugged in. Now I can relax. Okay, so I'm going to solve that and I'm just going to copy down and change my 55 that I had before. I'm going to change that to 132 and I got 8.28 to 2 decimal places. Now that's years. And I'll do the same thing again, but I'm going to change the 132 to 168. So 168. And that one's extrapolating. So we're predicting that that is a 12-year-old. There we go. All right. Which of them are most reliable? Hopefully you had a look at the 3 and you saw one of them is interpolation as opposed to extrapolation. So the most reliable one of those 3 is the 132 centimeter prediction. And if you need to say why, because, shouldn't put because at the start of the sentence, this is because the prediction was made within the data. That's what you can say. Whoa, what's going on here? The prediction was made within the data. You can use that word interpolation. Within the range of the data. You could even say that the others were extrapolation and they are less reliable. Therefore, interpolation. All right, one last thing that I would like to cover today, and that is looking at these things called residuals. Now, we talked about residuals not long ago. I showed you a little diagram, and the reason we talked about residuals was we use them to get the least squares regression line. And I mentioned, now I'm going to have to get rid of all this now. I mentioned that they are these little vertical lines vertical distances, in fact. It's not the actual line, but it's the distance that they represent between your data value, so between these, and the regression line. So I'm just highlighting them in green here. Here they all are. And etc. So residuals, as you can see, they're how far your data was from your line. Now, if we consider that the line is a prediction, they're basically your error in prediction. They're showing you how far off you were or how far off your line was. This is the error. So you see that sometimes they're referred to as these error in prediction. And the reason is, it's how far off was this line from the data that was here. In this particular video, I'm just going to show you how to calculate them. In the next video, I will go through them in a little bit more detail because we can actually put them on a plot, and I'm going to talk about what that means. So the error in prediction, what you want to do is you want to look at the difference between your actual data value and your predicted data value. Now this actual data value, that's what the dot is. That's what's plotted on the scatter plot. So this one will be given to you. Now it might be in a table, it might be on a scatter plot, it might just be given to you. They might just say when x is 5, the RV, when the EV was 5, the RV was 7. That's just telling you what it is. The predicted one, however, this comes from the regression line. So it comes from your equation y equals a plus bx, or whatever your least squares regression line is. So you actually need to find that first. So you find that by substituting into your rule. I'm going to do that with this one down here. We've got EV values, RV values. These might be called, of course, X and Y sometimes. In this particular rule, we've used RV and EV, so you've got that the RV is equal to this multiplied by the EV. So if we use the fact that we need to find the actual, well, we've got the actual, and we need the predicted, I'll show you what we would do to calculate a residual. First of all, you'll see this first one is saying for an EV of 3. Now, when you're calculating a residual, they're always going to give you the EV value because the residual is always an RV answer. So it's actually the RV unit that you're going to use because it's a vertical distance on the scatter plot. So if I do it with this one here, as you can see, to get my predicted value, what I do is I substitute my EV value that's given into the rule. So I'll do that now on my calculator. Negative 78.7 plus 28.7 by 3. Now I get 7.4. To find my residual, I need to also know the actual RV value. So if we have a look at 3 in the EV table, you'll see that the RV value was actually 8. So what I do to finish this off is I do my actual value minus my predicted value. So it was 8. It was predicted to be 7.4, so my residual is 0.6. And that's just to one decimal place. Let's do it again, but with a different EV. So this time the EV is 5. As you can see, to get my predicted, I put it into my equation. When you do that, I'm just doing it on my calculator now, I got here, so negative 78.7 plus 28.7 by 5. I got 64.8. I'm not going to round that off, just leave as is. Let's have a look what the actual value was. Go to EV of 5, actual value was 24. And there we go. Actual value 24, predicted 64.8. So into your calculator, and we get negative 40.8. Again, that's to one decimal place. So notice they can be negative. So you can get positive residuals and negative residuals. Talk about that more in our next video. Just a couple more. This time EV of 7. Predicted as usual. Type it in, and I'm just going to copy and paste what I had before, change it to a 7. I've got 122.2. I'll do the same while I'm at it with this one over here with a 9. So copy it across, change to a 9, 179.6. Now we need to know the actual value. So when it was 7, zoom up a little bit, it's a bit slow. When it was 7, we had a actual value of 77, and then we had for 9, 187. So 77, 187. And now I can finish this off. So the actual minus the predicted. The actual minus the predicted. And let's finish that off. So we've got negative for this one, of course. Oops, 45. And the last one, 187 minus 179.6, 7.4. All right, I'll finish there because we've gone on for long enough. The questions that I'd like you to do, I'll leave a list of them on the Google Doc, and we will continue with some residuals in our next lesson. So you'll have a little bit of practice covering some of the content that we've just done today.